Hi, this is Stephen Gray from Michigan State University, and I'm here with.
Allison Singer, also from Michigan State University.
And this is our second video in Introductions to Systems Thinking Using Mental Modeler. And when we left off before, Allison was telling me some very interesting information about how there are two different broad categories of models that we'll be talking about. Of course, is that all the number of models that there are? Or
Of
types?
course not. There's all different sorts of models, but for our purposes, it makes sense to just talk about these two.
And these two are slightly different from one another, which makes them two different categories. The first is this idea of mental models, which we'll talk about in this video, which are these informal models that we have in our heads about the associations in the world. And we use these things all the time to make decisions. And the second type of model is more of a formalized external representation of the world. And so mental models can be thought of as internal and informal, and scientific models are more formal and external. And one key piece of them is that they are related and interact.
So before you have a scientific model, you have to start from a mental model or multiple mental models.
And later, we'll talk about the super interesting fact that as you make a model, sometimes your mental model also changes. So let's start with the first type, which is.
Mental modeling. And what is that, Stephen?
That's a really good question. Well, there's the idea of a mental model dates back quite a while, actually. It dates back to 1943 with this guy named Kenneth Craik, who wrote in this book called The Nature of Explanation that the mind creates internal models of the external world, and that's how we are able to make decisions in all different contexts. And this idea was later further developed by Philip Johnson Laird from Princeton, who used this idea to understand kind of empirically how the mind works to predict the behavior of the external world by manipulating the internal mental model. So this allows us to do some pretty amazing things that we don't think about. For example, Allison, if I were to show you a picture of a pickle and some ice cream and ask you if you would like pickled ice cream, even though you probably haven't had it, what do you think you would say?
I would actually love to try pickled ice cream because I love all things pickled.
Now, have you had pickled ice cream before?
No.
So how were you able to make that decision?
Because I'm associating what pickles taste like with what pickled ice cream might taste like. And while I realize to a lot of people that sounds disgusting, to me, I would like to try it.
It's interesting that you're able to take ideas about what you know about pickles and ideas about what you know about ice cream, put them together, and be able to make a decision in a context that you've never actually been confronted with.
It is.
Mental models. And so we use this kind of model-based thinking in all sorts of different ways. We make associations between different things, like the sun is hot, in the world, and we use these in our heads to understand how the world works and make appropriate decisions within it. Now, one interesting thing about mental models is we use or communicate aspects of our mental models all the time while talking to people, but we usually don't talk about our assumptions that go into it. We just use our words to talk about these associations. And so in a lot of natural resource contexts, for example, models and associations are used to communicate different ideas about the world, like fishing pressure decreases fish.
Ah, okay, that makes sense.
And these are different, these are informal, we use these all the time, but they're related to this idea of scientific models. And when I'm talking about scientific models, in this case, I'm going to talk about computational models, these formal models that we use computers. Of course, you can think of a physical model of the solar system like you had in fourth grade as a model, certainly as a physical model of a thing. But when we talk about scientific models, I'm going to be talking about specifically ones that are used with computers. And there are a lot of different ways in which you can use models for systems thinking. And some researchers at CESYNC in Annapolis, Maryland, came up with different categories of ways that we can use models for systems thinking and to understand environmental problem solving. And the first category is qualitative approaches. Now, these do not require a computer. These could be a bunch of different types of representations of the external world. You could talk about qualitative scenarios, envisioning exercises where you're just talking about what you want the world to look like based on your your informal mental models, qualitative concept mapping, things like rich pictures. And for systems thinking in general, these things are good for problem identification. You can use these kind of qualitative associations that you talk about with other people to frame the nature of the problem you want to solve and identify cause and effect relationships. The second category is semi-quantitative approaches, and these are things like causal loop diagramming, role-playing games, fuzzy cognitive mapping, which is actually the theory and method behind Mental Modeler. And these are good for data collection about a problem, obtaining parameters and other important data. So we can move from kind of problem identification with qualitative techniques to semi-quantitative approaches with any one of these techniques. And the final tool for systems thinking is quantitative approaches. So these are more kind of higher order models that definitely require a computer to do. Agent-based modeling, system dynamic modeling, Bayesian belief networks. And these are really good for analyzing a problem as a series of interacting parts, as a system. And these can usually also be manipulated to run in what-if scenarios about the system dynamics of a problem. But some of these are easier to use than others. Some of them require more time, some of them accept empirical data, some require training of the modelers or the people you're working with, some have time aspects and some have space aspects. And so a general rule of thumb as you move from qualitative approaches for systems thinking to quantitative approaches, which are these computational approaches, the qualitative approaches have lower training, and so they're pretty easy to use, but they have lower analytical capabilities. And the more quantitative approaches require kind of a lot more training, but they have high analytical capabilities. With Mental Modeler, it's kind of right in the middle.
It's like the Goldilocks.
It is like that, just like that. That's a great way to talk about it. So what I'd like to do now is talk about examples of each one of these as a way in which we can engage with these tools for systems thinking. And we'll talk about rich pictures, which is qualitative, causal loop diagramming, and then system dynamics model. And for this one, we're going to choose all models to understand systems from the food system. So on the left-hand side, you see how this is a rich picture, we'll talk about in a second, of obesity. The middle picture is a picture of a causal loop diagram, which is semi-quantitative. And then on the right-hand side, you have a system dynamics model. These are all of food systems, not the same food system. But you can see how you can kind of move from one system representation, a model, to another. So let's talk about rich pictures. What are rich pictures, Allison?
Well, it looks like they're kind of whatever you want them to be, but I see some sort of pizza and some soft drinks, and they're connected by these arrows, which I assume are relationships between these different concepts that people have drawn out. We've got villages and cities. So I think it looks like to me that you're just kind of trying to organize the different images in your brain into a system that makes sense and lets you identify how these different concepts and images are connected.
That's exactly what they are. So you can pull ideas and concepts from your brain, like, I guess that's America, when it only had 9 states. And you can see its relationship to Canada, which interestingly is not a flag, it's just the word Canada. So the representation of the things can be any kind of thing that makes sense to you, that you're pulling from your mental model, right? And you're showing what the relationships between these different concepts are. So these are fun to make, and also, they're artistic.
Yeah, I like the looks of these. That's about my skill level.
Well, let's go up a little bit and talk about semi-quantitative. So causal loop diagramming, you could just translate a lot of these pictures into words and then talk about positive and negative relationships. Now, you can put numbers on these too, like you do with fuzzy cognitive maps, but in some of these things you can see, so at the very top you see land agriculture used has a positive effect on food production. And on the left-hand side, you can see that agricultural capital also has a positive relationship for food production. So whereas in rich pictures, you can draw whatever you want to, and the relationships can be one of many, in this particular case, you're going to be a little bit more constrained because these words need to be stocks that can go up or down, and the relationship can only be positive or negative. It can't be kind of anything goes like it is with a rich picture.
Yeah, and it looks like these you could actually add data to and then turn it into a quantified
Oh my,
model.
don't get ahead of me, Allison, because the third type of model, as we mentioned, is quantitative modeling. And whereas these relationships in a causal loop diagram are pretty easy to define and easy to use with people, they're largely linear relationships. One thing has a positive influence on another or a negative influence on another. With this type of system dynamics model, you can put in very complex relationships. And so this is just a further expansion. You can kind of see that all the stocks, again, are going to be words in this case. So agricultural revenue can increase or decrease, agriculture investment can increase or decrease, GDP, and so on. But the relationships are positive and negative, but they can also include feedback loops and also include differential equations. So that's right. So and then what you can get out of this is a pretty good understanding of how all of these pieces interacting together can predict outcomes based on whatever variable that you define under a range of what-if scenarios.
Okay, so I see on the right there we've got sort of outcomes over time, it looks like.
Under different what-if scenarios.
Interesting.
Isn't it? And what I like about then we don't really think about that much, but as scientists, we have usually these mental models about how the world works or some hypothesis. We can offload that understanding from our mental model and represent it explicitly within a computer, kind of mix that with information, empirical data about the world to refine our model. But what's really interesting about the modeling process is the process of making and refining a model actually changes our original mental model because we're able to offload a lot of the complexity that we can't hold in our heads.
That's great.